Alright, okay. So this is hopefully a quick little video to screencast to put my ideas so they can be communicated easily without typing a whole bunch of a long document and a lot of diagrams. So anyway, this is some ideas on intersection theory and intersection theory for some ideas here in HeeksCAD. With this, we're starting out with polygons right now to do some intersections of 2D things for sketches and other things. There's lots of things that we need 2D intersections for. Perhaps this could even extend to 3D. But what we have here is, this is a simple example. We have two triangles, and we want to do Boolean operations on them. We want to do unions, differences, and intersection. Unions, differences, and intersections. Yeah, those three operations. And we want to do them very fast, very quickly, so that we can do a lot of neat things to make updating of features and sketches and 3D models fast and responsive. What I'm doing this in is, I'm doing this in the context that John Pry has come up with some code that comes and finds all the intersections and splits up all the line segments at their intersections, and then it comes through here and builds a graph of the intersection points, or as nodes in the graph, and the edges are the way to get from one node to another. So here, from intersection 1 to 2, say if we look at this 3 hash line with the 3 hashes in it, it's the way to get from 1 to 2, like that. So at first I didn't think that was going to be terribly useful, but it turns out it's actually tremendously useful. I think that we can very, very quickly calculate these Boolean operations once we have this information. So the first thing that I want to talk about is finding the exterior region. There's this whole area outside here, which is a region that's not of interest to us, except to know that it's the exterior, infinitely huge region that's outside of the shapes that we're considering. So I thought of some different ways to find that, winding numbers and integrating area and stuff like that. I think I like this alternate way quite a bit better. If we go through and we find the minimum y, or the maximum y, maximum x, minimum x, whatever, we can adapt the code for this, but I'm going to talk about it in context of the point that has a minimum y value. If there happen to be multiple y values, it doesn't matter, we pick one of them, and this will work no matter what. And from that point, all the line segments that exit from it, we measure their angle from the horizontal axis. Then we take the line with the minimum angle, not magnitude, but magnitude inside, so the the line extending with the minimum angle. So in that case it happens to be this line. And then we could, especially here with polygons, we could guarantee that this is an edge, an exterior edge of the shape, of the combined shapes. So it's of interest to us. And we can also guarantee that the region, the infinite region, is to the right of this line as we extend away from that node. So we guarantee that this edge is an exterior region. And if there are no nodes, this edge all the way to all the nodes is guaranteed to be an exterior region as well. But let's say we walk along this line, this line segment here, and whenever we get to a node, we choose to follow we have this angle here in between these two nodes, and we choose to follow the one that keeps the region, the exterior region, to the right. See, I might have said left here. So we extend here, the exterior region is to the right. So we follow this around, and everywhere we have to make a choice, we choose to keep that exterior region on the outside, and we can follow and know that all of these edges are in the exterior region. So that's the 4 hash line and the 3 hash line are in the exterior region. So if we were to be doing a union here, this is incredibly simple, because all the way, that's it, we're done. That's all it takes. So that we have the actually concave hole, the exact concave hole of this polygon, and that's all that we need to do. But if we continue on, there's some more things to see here. I want to talk about these intersections a little bit more, these nodes in the graph. If we look at them here, an intersection node will have the possibility of having regions attached to it. So in this particular case, this region that I've labeled A here is the infinite exterior region. We can make note that in intersection 1 that A here is the infinite region, and D here on intersection 2 is the infinite region. Now, we have as many possible regions extending from this node as we have line segments coming into it. Now, there are no fewer than 3 line segments that come in, but there can be many that could come into the infinite number that could come into a node. Now, hopefully we don't run into too many cases like that. I don't imagine that we will. But anyway, we have these possible regions that extend from here. We found the exterior region, and so we'll exclude these 2 regions here from our searches here, from the rest of our searches. But let's start here at node 1. And we've eliminated A, so we're going to